Hello, here are some results for the Bernoulli gripper project. It may be best to actually watch this video first so that it sort of makes sense what's happening when you're building the simulation, but I don't know. So first, some background. The Bernoulli grippers use the airspeed increase that happens right here as the air flows down this device and gets shot out the side to actually pick up an object without contacting it. So it's used for delicate stuff, say solar panels or some food handling applications, but it's sort of an interesting physics problem. So we did some theoretical calculations. A lot of this was from a paper, some of this we did ourselves. But basically you end up, you go from Bernoulli's equation to a lift force that you expect upwards. And this is a subtraction of the force you expect from the low pressure region created right here, where because of the air velocity going way up, so pressure goes way down. But then you have to subtract out the force of the jet impinging on the surface. So right here, there'll be a force downward. So subtracting those two, you get the net lift up on your substrate. So how we did the simulation in Ansys, the x-axis is how you have to do axisymmetric simulations. So if you can visualize this here, the substrate is highlighted here, and then the gripper is highlighted here, and the enclosed volume is just the air. All of these parameters are picked specifically so that we could later do a simulation using a CD as the object that we were picking up, and another CD actually as the top plate. So all of these dimensions are not totally arbitrary. So first, the static mesh results. You see kind of what you expect to see with velocity. Velocity is moderate here and then picks up really high right there, right when it meets the substrate and has to get forced through that tiny opening. And then it looks like mass is not being conserved here, but because axisymmetric, the area that the flow is going through goes way up. So the velocity goes down there. And then over here, you see the low pressure zone, which is what's picking up the CD. And then the high pressure zone, which is that impinging jet that we subtracted off. And doing a parameter sweep of inlet velocities versus suction force, and this was just with a static mesh. The simulated and the theoretical, so this is the blue lines from Ansys, and the yellow or the orange line is from an Excel sheet that ran this equation, and that we had very similar results. And the theory was, which we sort of showed later, was that the simulation showed lower suction force because of the boundary layer effects, like along the edge here, slowing the air down. For dynamic mesh, we use a 6 degree of freedom body, but constrained to 1D motion. You put gravity in the positive x-axis going down here. And then the axis mesh needs to passively deform along this line. And then this mesh here needs to deform as the CD is able to move. Too many cycles or too sudden of changes in the mesh lead to mesh failures. It'll say negative cell volume. The mesh can't update fast enough, and it will crunch to look like this. and then the simulation crashes. So for results, with the dynamic mesh, it's sort of an interesting oscillatory motion if you tweak the parameters just right. You can see it getting picked up and then put down. And this is all at the very beginning of the simulation. This sort of stabilizes and finds an equilibrium eventually. And we actually made a physical model of it, and this does work. And sometimes it's kind of tough to control exactly, but sometimes you can hear the oscillation motion. And then this is just breath powered. So the pressures that we picked are actually, you're able to produce that just by breathing into here, and it will pick up the bottom CD.